So we deal with these two right here. Specifically, mostly this one. Yes? Yeah, don't even ask. Just go ahead. Yeah. Okay. Electromagnetism, because it's used so often, we don't usually call it that. What we typically do... What's that? Yes. No. All right.
Are we recording it? Oh.
Electromagnetism is what I've kind of given it this name. I've heard different things, but we're going to call them pseudo forces. If you've ever taken Latin at all or know anything about the word pseudo, it stands for fake or false. And it's not to say that these forces don't exist. It's just they themselves are not new forces. They are just specific situations of electromagnetism. The first one we already kind of started talking about, so we'll continue from here, and that's going to be friction.
Are these all under electromagnetism?
Yes. Actually, let me write that up here. Pseudo forces are basically names for situations of electromagnetism. I'm running out of room. Force friction has, yes?
What is that? Is that FR?
FF, I'm sorry, force friction. Force friction has two types, one of which we've already talked about. The first type is surface friction. Surface friction has to do with when any two objects whatsoever come next to each other, and that's exactly what we talked about a moment ago. When the protons and electrons try to hold on to one another, that's what we call surface friction. So it occurs when you try to take your hand and run it across the table. It happens when you take a paper, run it across the table. It happens if I even take this marker and I let it fall down the wall. Anytime two materials are in contact with each other, the protons and electrons are holding on to one another, and that's surface friction. It's if you drive down the road, or actually a great example of surface friction is if you ever try to slide across the table, or well, not the table. This is not the table. That's the table. The floor, right? You try to slide across the floor. Those electrons and protons try to hold on to one another, and because of that, of course, you try to stay. It holds you in one spot. And depending on what kind of shoes or socks you have on, there's less of a hold between protons and electrons, which allows you to slide farther or not nearly as far. Second type of friction that we typically hear about is known as air friction. So you know how sometimes you have to walk down the freshman hallway?
Yeah.
It's not preferred, but it happens every once in a while. You know how they're all tiny? And you just run, walk over them essentially. You just walk. Yeah, what are you doing? Because I'm not entirely positive that they're real people, but you run over them, right? But they still slow you down a little bit, right? And the reason why, of course, is because they have electrons in the side and you have electrons. So anytime you make contact, they push you back and you push them forward, right? Well, go a little bit smaller. What about water? Well, water has mass too, right? It's the same situation. It has mass, it has less of it, right? But there's more compact. And so when you try to walk through water, of course, it pushes you back the opposite direction because electrons and electrons, still electromagnetism. Same thing is true, of course, of air. Air is one of the more difficult to see because we deal with it so often, and to us we forget that it's even there sometimes. But when I walk through the air, I'm running into small amounts of mass, right? So which way is it going to push me?
Opposite way.
Opposite way. Very good. So that's always going to happen with air friction. Now, air friction will very much be affected by the velocity of the object. How come?
Because if you're going with a lot of force, then they're also coming...
A lot of force or a lot of velocity?
A lot of velocity.
Right.
Then they're also coming at you with a lot of velocity, and that translates into a lot of force.
You're right. There's probably a little bit better way. That's a good way to think about it. But there's probably another way that probably makes it a little bit more easier. There we go. You run into a bunch more atoms. The faster I go, the more atoms I run into. Just like with friction. If I go faster, I'm going to run into more friction, which means more pushback. Right? Okay. Like I said, the relative velocity, that's an accurate way of looking at it as well. And I'm not saying you're wrong, I'm just saying it's a slight better way to look at it. Okay. So, air friction, and you can see, once again, electromagnetism. Real quick with friction, okay? Which way will friction always point on an object?
Opposite way.
Opposite of what?
Where it's going.
So opposite of velocity, right. If you think about air friction, if I'm going this way, which way is it going to push me? And if I go this way, and if I jump, and if I fall back down, exactly. So no matter which way you go, air friction will always go the other way. Same thing is true of surface friction for the same reason, okay? Well, not the same reason. If I take my hand and I slide it across the table, they're holding on to me, right? Which way are they going to be pulling? Towards themselves, right? Well, if I'm going this way, their selves are going that way, right? So they're going to be pulling me back always. So if I try to push this way, my hand's being pulled back that way, and vice versa. So, that'd be a good thing to write down. Friction always goes the opposite direction of velocity. Number 2 is what we call force normal. Force normal is, once again, another force that we've actually somewhat already talked about. Okay? It's when you have a solid object and it pushes the other way because of its electrons. So right now, we would say that every object on this table is being pulled down because of gravity, yes? And why are they not going down? What's that?
Because of the electromagnetism.
Because of the electromagnetism in the table pushing up. We'll call that force normal. It's anytime you have a solid object that is going to push the other way on another object. So like here, the table is pushing up. And someone goes, wait, the marker here is pushing down though, right? Isn't that force normal? Well, yes it is as well. We'll talk more about that probably tomorrow. If I try to run full speed through the door, will I make it?
No.
How come?
Force normal.
Force normal, but specifically in electromagnetism, what's happening? Repelling because
it has electrons.
electrons here, electrons in the face, right? So as soon as I smack the face into the door, it's going to push me back, and I'm going to push the door this way. Now, who's going to win?
The door.
Probably the door.
Because it has more.
Feel the whole.
That's a good point, and that's actually very true, and that comes in much more tomorrow. That's right. Yes.
Okay, so what is the main thing that you're describing? Like, is it like that they hit off each other and go opposite ways, or like, you know what I mean?
Yes, I do. Okay, the main thing you're describing is the same thing for all of these. It's when the electrons and protons interact. So the different names that we're putting up here is a specific situation where this occurs. Okay? So, like I said, the situation for this is there's some solid object just pushing back on the object trying to run into it. So if I were to jump, if I were possibly able to jump high enough to run into the ceiling, which way is the ceiling going to push me? Down. We would also call that force normal. Okay? If I had something on a ramp here, let's create a ramp out of this, right? Which way will this push? Not up. Angle, like that. Right? It always goes, and this is because there are electrons and electrons pushing. Okay, watch this. Which way will it push if it goes this way? That way. If it's on the side, if I push it against here, it's going to push this way because the electrons, right? And you can keep going all the way around. So how does the force normal always go compared to the surface? Probably, opposite probably isn't the best word. Probably there's a math word.
90 degrees.
Perpendicular. Very good. Perpendicular, 90 degrees to the surface of the object. So that's force normal. So that's Fn.